Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about feedforward model-based control. As an engineer, you've spent years learning how to model processes, heat, mass, and momentum transfer, thermodynamics, chemistry, etc. And you've learned the math and computational tools to make predictions. The practice of process control can seem oddly separated from all of that knowledge. We use some limited dynamic models, often empirical rather than first principles. But when we apply feedback control, we only require a knowledge of the present process state and a pretty basic knowledge of which direction and how much the state will change when we manipulate our controlled flows. We design processes with detailed models that predict how they will operate, but then we don't use those models for control. It's a bit like navigating through a city by trying to keep an eye on a landmark in the distance when we could be using Google Maps. There are several reasons for this. For simple, fast feedback loops like flow, pressure, or the temperature leaving a heat exchanger, a basic knowledge of dynamics is quite sufficient for excellent control. Second, we design processes largely with steady-state models. Steady-state models don't describe everything we need for dynamic control. And lastly, until the last decade or two, real-time computation was expensive, and process control computing devices were not designed to facilitate it. But there is a group of control problems where there are slow enough dynamics that control is challenging, and where even a steady-state model estimate can greatly assist our feedback controllers. The manner that we'll do this is labeled feedforward control in textbooks, but I prefer to call it feedforward model-based control or model-assisted feedback control to link back to our chemical engineering models. Let's look at an example. Here we have a distillation column with a controlled feed and composition control inferred through top tray and bottom tray temperatures. Our model of the column, perhaps through Aspen or ChemCAD, tells us that for a 10,000 kilogram per hour feed, we'll need 806 kilowatts of steam heating in our reboiler to achieve the desired bottoms composition and bottom tray temperature. Fair enough. I can put a flow meter and flow controller on my reboiler steam, and I can use a steam table to translate kilograms per second of steam to kilowatts of heat and deliver those 806 kilowatts of steam for every 10,000 kilogram per hour of feed. Will that yield accurate and reliable control of my bottoms composition? Probably not. The software is modeling an idealized column and reboiler, not the real one in front of me with disturbances, inefficiencies, and actual process dynamics. It's nice to have an estimate, but I need feedback based on measured state variables to give me reliability and accuracy. How do I deliver both? Effective feedback control of a bottom tray temperature with reboiler steam has slow dynamics, so using a cascade design with steam flow as a subordinate loop is recommended, as was discussed in the chapter on feedback control. That makes the output of the supervisory temperature controller the set point for the subordinate steam flow controller. We can incorporate our model prediction by adding a bias signal to that supervisory control output, where the bias signal is the measured column flow rate multiplied by our steady-state model prediction of 806 kilowatts per 10,000 kilograms per hour of feed flow, with the kilowatts of steam translated into a steam flow in kilograms per second. The remote set point going to the subordinate steam flow controller is the sum of the model-based steam flow necessary and the output of the supervisory controller's feedback loop. It's helpful to look at this as a function block diagram. The top two rows describe a normal cascade controller with the subordinate steam flow controller FCE2 and the supervisory bottom tray temperature controller TC-C1B. But on the third row, we have the column feed flow transmitter FT-C1F. Its signal in kilograms per hour is multiplied by a ratio that represents our model estimate of how many kilograms per second of steam will be needed per unit column feed. The output of that math block enters the PID controller as a bias, which does not alter the feedback math in the controller, but is simply added to the supervisory controller's output. What are the advantages and disadvantages of this feed-forward model-based control? First and foremost, the model will anticipate and act to accommodate the changes to reboiler steam demand that a change of column feed flow would entail. With only feedback, an increase in column feed rate would cause a dip in the bottom's temperature, which the slow feedback temperature control on its own might take tens of minutes to react to and reject. Even if the model prediction is only 90% correct, that dip due to the feed change will now be 90% smaller with the addition of the model. And the feedback controller is still there to achieve that last 10% of the control needed to maintain the precise bottom's tray temperature. Even better, with the model doing 90% of the control, you'll find that you can tune that supervisory feedback controller more aggressively, as there is so much less to do that it has to do by itself. There are only two real disadvantages. First, the steady state model may actually react to the change too early relative to the process dynamics. But anticipating disturbances is rarely a problem relative to reacting slowly to them. Second, you need a model to put this scheme in place, but lack of a model is a solvable problem. If you lack a first principles model, observation of an operating process should yield an empirical relationship to allow a feed-forward prediction in the same way. Here's another example where a model-based feed-forward solution can be applied. This is a hydrochloric acid absorber, where gaseous HCl is absorbed into water to form hydrochloric acid and a great deal of heat. Because of the heat, HCl absorbers are most often graphite heat exchangers. Water and HCl are added concurrently and absorb as the heat is removed. The process goal is to maintain a constant acid strength at the outlet of the absorber by adjusting the water mass flow to ratio to the incoming hydrogen chloride mass flow. Because the HCl is coming from several batch chlorination reactors, the HCl flow varies. The acid strength leaving the absorber can be estimated accurately by measuring its density, but there's a lag of several minutes between adjusting the flow of water and seeing a change in the outlet acid strength due to liquid transport time through the absorber. The water flow is controlled in a cascade arrangement with a supervisory slow acid strength loop supplying a remote set point to the subordinate fast flow loop. Our opportunity to use a model stems from our knowledge of how fast chlorine is being charged to the various chlorination reactors that feed the absorber. If we do a mass balance, the mass flow of HCl byproduct from the chlorination reaction, it'll be 1-to-1 by mole, will be proportional to the mass flow of chlorine by the ratio of molecular weights. And the strength of the acid percent AC will be, that's coming out of the acid absorber, will be defined as stated here. Combining these two equations and solving for the mass flow of water, we can find that as a function of the mass flow of charged chlorine. So we get this formula, which is a function of the desired acid strength. When we take this model and add it as a bias to the supervisory acid control loop, all but the fine-tuning of composition will be achieved through use of the model. And if anything, the water flow adjustments will anticipate, rather than lag by minutes, disturbances to the HCl flow and acid strength. In this process, strong acid is highly desired, but insufficient absorption of HCl threatens an environmental release. So, model-based enhancement of the control of a difficult dynamic problem solves a critical operational concern. Opportunities for feed-forward model-based control require the following process characteristics. 1. There is a dynamically slow or difficult to measure process variable which is key to some objective. 2. We can assemble a model, either steady state or dynamic, to predict that variable with model inputs from other measured variables, especially variable sources of disturbances. 3. One of the model inputs is a flow that we can manipulate to remediate the disturbances. The major obstacle in not using more model-based feed-forward control in process plants is a failure to appreciate the opportunities and to communicate them between the chemical engineers with the models and the control engineers who can implement the design. It takes a process engineer who understands control system design to seize these opportunities for improvement, which are most certainly out there. Model-based feed-forward control should be much more widely used in the process industries. Look for full text, exercises, and more videos at chemicalengineeringpractice.org. Find videos on YouTube by searching for Process Control Design and Practice. Like and subscribe. I'm Tom Meadowcroft. I hope to see you again soon.